So hello and welcome back. We have seen so far two very excellent problem solving techniques. One was called as the artificial neural networks, wherein we discussed how analytics of the brain results in some very fantastic models that are ultimately used for problem solving. The other, of course, we discussed the paradigm of evolutionary computing, under which we discussed this algorithm called as the genetic algorithm, and we said how it is able to evolve the system, how is it able to optimize the system, how is it able to completely make a system starting up from, let's say, random systems to some very good systems that solve some very good real life problems. We will continue the discussion over evolutionary computing much later on when we see the other algorithms that come under this class of evolutionary computing. But before that, we will touch upon the third pillar of soft computing. We will touch upon the third very important algorithm used in soft computing, and that is about fuzzy logic. So there is some kind of logic attached to it. There is some kind of intelligence attached to it. There is some kind of problem solving methodology attached to it the moment we say logic. So let me say what simple logic can approximately be. That I just say that by some kind of logic, I know that there is a rule that we all follow in our daily lives. There is a rule that we all obey, and that rule may simply say that I say that if it's raining heavily, if there is some kind of rain and that rain is heavy and I say roads are very bad in nature, the roads are not good, then I say it's very risky, then don't drive. So without some understanding we can formulate these kinds of logic, we can formulate these kinds of techniques, we can formulate these kinds of rules, and then we can go about using all this logic that is inherent to us. We can use all this kind of logic that is inherent to us, and we can make some kind of decisions. Every day we make hundreds of decisions. Of course, that is on our understanding intelligence, that is using all the information that we already have, but above all, that is using some kind of logical relationships that we can formulate between entities, between states, between conditions, and using all those logical relationships, we are able to do all kinds of decision making in our daily life, whether to do something or not to do something. If you do something, then again the state of the system changes. There are some changes which ultimately lead to a series of more logic, and therefore one logic, its actions followed by another logic, followed by a third logic, sometimes a combination of logics, using all this kind of logical relationships, using all this kind of logical inductions, using all this, we are able to do a lot many things in our daily life, and that is what makes a human intelligence. We are all logical beings. We all know what to do, we all know what not to do. Based on all this understanding that we have got out of our own, based on all this understanding, we can take numerous decisions in our daily life. A lot many managers at the medium top any level, they use some kind of logic to decide what should be the next business move and so on. So the basic thing is that in our daily lives we are using a lot of logic. We're using a lot of logic. Can we make in machines in which we plug in some kind of logic and they are able to solve problems? They are able to solve some kind of problems. Now of course we are not discussing how do we induce in this logical module inside the machines and they are able to decide. It's a very trivial thing to do. It's a very trivial problem to solve. And of course, that we have already seen by simple programs, by simple techniques, you can always give in some kind of logic inside to the system. You can always have some kind of induce right inside your system, and using these rules, your system is able to make decisions. Of course, there's a human who codes these rules, who plugs in these rules, whatever the system, whatever the machine may be, whatever the language may be, whatever the platform may be, you all can always plug in these rules inside the system working, and the system will be able to make intelligent decisions, the correct decisions. So that is not what we are supposed to do here. So what is it that we are supposed to do over here? Now, for that, we have got this beautiful word called as fuzzy. So first we see into this hour of lecture, or even the next hour of lecture, is that what this word is fuzzy all about, why do we need it, what are the limitations of this system that I just talked about, and how do we go upon proceeding with inducing some kind of fuzziness into the system that we already have. So the word of discussion would be fuzzy. Now let me again come up to what is known as the set theory. We have been taught a lot many times that there is a universal set U that contains all the entities possible in the entire universe. That's why it's called as a universal set. A set A is defined by all the elements that are contained inside the set. So let me say here I'll have some very good definition of A. Which will be like this. E1 belongs, E2 does not belong, E3 belongs, E4 belongs, E5 does not belong, E6 does not belong, E10 does not belong. There is a very, what we call as a crisp definition of the set A. An analogy would be that, let me say, there is a universal set known as temperature. So what my temperature set would contain, it would contain all numbers between -infinity to infinity. Of course, many of them would practically not be possible. I say that there is a set hot inside this fuzzy set, and it has got in temperatures of, let's say, anything more than 35 degrees hot. There is another set cold, so I say anything less than 20 degrees is cold, and there is a temperature known as moderate, which means anywhere between 20 to 35 is moderate. So like this, what I got very good definition of the set temperature. So let me say this was some -infinity, this was infinity. This is what is called as cold, this is what is called as hot, and this is what is called as moderate. So there's a very perfect, there's a very crisp definition of temperature. There's a very crisp definition of temperature, and that is what the set theory that we've dealt with. That's what the set theory that has been taught to us in all the various courses, that is what it says. What fuzzy sets are about is that can we make these boundaries not crisp, but rather fuzzy in nature? Can we make them in a lingual sense a little vague in nature? So a fuzzy set is again a set U, which of course has some E1, E2, E3, E4, E5 and E10 over here. It is again a universal set U that has got all the various elements inside this, but the only difference is that all elements belong to all sets. So if I use the term A, if I use the term A, it will contain not one but E1, E2 up till E10. It will contain all the elements. set A, E1 belongs to the degree mu E1, E2 belongs to the degree mu E2, and E10 belongs to the degree mu E10. So this is what the definition would be. So let me say again, I have to take in, I'll draw in some kind of boundaries over here. Again I need to define the set A over here. Now this boundary is not defined right now. It's not defined right now, so that's why it's very vague in nature. So I say that there is a same element A. E1 belongs up to the degree of 0.7. It's a probability measure between 0 and 1. E2 belongs to the degree of 0.8. E3 belongs to the degree of 0.65. E4 belongs to the degree of 0.5. E5 belongs to the degree of, let's say, 0.2. E6 belongs to the degree of 0.1. E7 belongs to the degree of 0. E8 belongs to the degree of 0, and so on. E10 belongs up to a degree of 0. This is what my definition of A would be. Now remember, that is containing all the elements in a universal set. It contains all the elements, but the degree is varying. So if I just draw a dotted line, if I just set a threshold and I draw a, let's say, 0.5, and I say that only selected elements whose degree of membership is more than 0.5, so therefore I'll have this kind of, I cannot draw a solid line over here because this is not what the definition A is. I draw a dotted line over here, and that's what I said by this line is not crisp in nature, it's not solid in nature, it is fuzzy in nature. It's a very vague kind of a boundary. I change the threshold to 0.6, it will contract, 0.7 it will contract, 0.1 it will expand. So the moment I change the threshold, it will change. So therefore what can sometimes be represented as a color notation where the intense colors they associate, signify a high degree of association, and the more not intense colors, the weaker kind of participation of any element EI towards the set. I'll get in this beautiful curve that I get. That will denote the spatial distribution of this element A, where the membership would be varying in nature. I can again plot the membership as axis, and I can get how the various elements are distributed. What this is known as the membership function. This is known as the membership function, the mu of EI. So what mu of EI denotes is that the membership function mu of EI denotes the participation of EI into the set A. Sometimes the notation is for the jth kind of membership set that we are dealing inside this universal set. For the jth set that we are dealing inside the set, the membership function mu x denotes how much x belongs to this set J. It denotes how much this set X belongs to this set, how much this element X belongs to this set J, and of course not to mention it's a probability, it's a membership value, it can always lie between 0 and 1. Membership value of 0 means the element is completely out of the set. 0 relationship that it has with the set, it's completely out of the set. Membership value of 1 means it's completely inside this set. Its membership value is 1, it has complete relationship with that set. It is completely a member of that set. So that's why the membership value, it will lie anywhere between 0 and 1. So again, let me wrap this up. Let us go up to the same temperature kind of problem over here. Let me again touch upon this very simple problem over here. Now I cannot define these lines. I cannot define because hot will also lie between minus infinity to plus infinity, cold will also lie between minus infinity to plus infinity, and moderate will also lie between minus infinity to plus infinity. The only difference is that the membership value, the association value will be different. The association value will be very much different in nature. And how much that is different, that denotes that is what we are supposed to find out. So again, let me say what happens in this kind of problem is that I say that I need to define a set hot. I say I need to define a set that is hot. So all that I do is that let's say this is some 30 degrees Celsius. I needed to define something called as hot. So all I say that any temperature above 40, its degree of hotness is 1. Its degree of association to hotness is 1. So therefore the kind of set that I am denoting is that 40 degrees centigrade, 41 degrees centigrade, 42 degrees centigrade, they all will have a membership value of 1. To a degree of 1, they will be called as hot. But if I have something like 35 degree over here, its membership value will be 0.5. Its membership value will be 0.5. That means that to a degree of 50% or to a degree of 0.5, I regard 35 as a hot temperature. To a degree of 0.5, that is where what I regard it as a hot temperature. For anything like 29, 28, 27, I say they are hot to a degree of 0. The degree of hotness is exactly 0. So that is that whenever I talk about something called as hot, 29, 28, 27, 26 degrees centigrade, they are not perspective, they are completely outside the set. And that is what my definition of set is. That 30 will belong to a degree of 0, 40 will belong to a degree of 1, 41 will belong to a degree of 1, and so on. Similarly, I say that there is something known as moderate. Let me do it something like this. Let me say this was more moderate. For a temperature of 30, I'll say that the temperature 30, the element 30 belongs to the set moderate up to a degree of 1. Up to a degree of 1, it belongs to the set moderate. But if I say some 35 over here, to a degree of 0.5, it belongs to moderate. If I say 25 over here, to a degree of 0.5, I call it as moderate. So therefore, every temperature has some degree of belongingness to the sets that we are defining. We are trying to define 3 sets over here. Now the only difference between this problem and this problem is that here the elements were non-continuous in nature and here the temperatures are continuous in nature. I have infinite points between any 2 points over here. They are continuous in nature and these were non-continuous in nature. So I am trying to define 3 sets over a continuous domain. I have defined 2 of them. Let me say the third one is defined like this. Here I say that anything from minus infinity to 20, it has got a membership value of 1 for cold. This was cold, this was hot, and this was moderate. So at temperature 19 degrees centigrade, 18 degrees centigrade, it will have a membership value of 1 to this set called as cold. it will have a membership value of 1 to this set called as cold. My 25 degrees centigrade, it will have a membership value of 0.5 for this set known as cold. So for any temperature T, I'll basically have 3 membership value. Let me again take up a random temperature, let's say 38 degrees centigrade. Now this 38 degrees centigrade belongs to all the 3 sets that we have defined. We have defined 3 sets, hot, cold and moderate. It belongs to all these 3 sets. To the set hot, it belongs to, I'll check up over here, 38 will be something out here. And this is the hot temperature, so its membership will be something like 0.8 over here. So it belongs to the degree of 0.8 to the set hot. Let me say how much does it belong to moderate. Moderate, this is the membership function, this is the point. Let me say this is 0.4. So to a degree of 0.4 it belongs to moderate. Cold, this is what the membership function is. So here I'll extrapolate, it will come out to be exactly 0. Cold, it belongs to a membership degree of 0. So for any temperature, I can find out the 3 membership value of these 3 sets. Let me again take it a temperature, let me say 15 degrees centigrade. It belongs to HMC, all these 3 of them. First of all, I find out what is the degree of belongingness to hot. This is what is the membership function of hot, and this is where 15 degrees centigrade is located. So the membership value is here, it's 0. Moderate, this is what the curve is. This is the curve for hot, this is the curve for moderate, and this is the curve for cold. So this is what the curve is. So again here, 15 degrees centigrade, the membership is 0, and cold, the membership is 1 over here. This is what the curve is. The membership degree is 1. So basically for any temperature T, I can find out the 3 membership values. To hot, to the set hot, to the set cold, to the set moderate. So let me say that my membership of hot at any temperature T is what is called as mu hot T, a mu cold T, and of course a mu moderate T. These 3 are called as nothing but the membership functions. It's sometimes noted as the MF, the membership functions. What the membership function does is here, that given any temperature T, that whenever you try to give in any temperature T, it will try to find out what its membership value is about. You give in any temperature T, it will find out what is its membership value. And this is again what the same notation was what we wrote down over up here. It's mu, we suffix, we prefix or we postfix the membership function it is denoting, and then in bracket the inputs that it's working upon, the temperature T. Now we have discussed the membership functions, the entire concept of the fuzziness and the membership functions. We have discussed what I discussed was known as the fuzzy sets. The fuzzy set, they denote sets defined again as per the set theory as a subset of the universal set U, where every element belongs to every set to a different degree. And this degree is called as the membership value. It's like a set and every element takes in a membership and a different level of membership. So every element belongs to every set in this fuzzy set theory. The degree to which it belongs is called as the membership value, and the functions that for any element E, they give you a membership value for any set A are known as the membership functions. So that was all about the fuzzy set. Now, why is it that I have to go from my normal logic system and I have to go from my fuzzy set system? I have to disregard my normal crisp sets. I have to disregard those fixed boundaries, and I have to go with those vague kind of boundaries, which which are of course called as the fuzzy set. So why is it? Now we work extensively over these kinds of rules. If let me again say, take the same example, if rain is heavy and road is bad, then don't drive. Or let's say I say then drive is unprobable. I work out these kinds of rules. I work out these kinds of rules over here. So again, what the people want to know about the logic kind of theory, they would say is that people want to know all those kinds of logical theory, logical analysis would say that this is the kind of logic module that has been inbuilt into some kind of a system, and what they say is that please measure rain. How much is the rain? So it said that it's raining to, as officially measured, the rain is presently 10 centimeters. So they say that rain is low, that means you can drive. That means in the system you can drive. But suppose let's say that rain is 11. Now my system is regarded as a high rain area. Even though it rained only a centimeter more, had it rained 11 centimeter, it would have been regarded something as a high rain condition. And therefore suddenly when it comes from level of 10 centimeter to 11 centimeter, the moment it rains 1 centimeter more, suddenly I got my alarms up. That don't drive, suddenly all the alarms are up. I'm of course assuming that the roads are bad. So there is that the alarm will suddenly get up, and then all of a sudden will be up that now you're not supposed to drive. So that's what the decision is all about. But of course in reality it doesn't happen like that. In reality it would be that if it rains 10 centimeter, then of course I'll take in some precautions. If it's not raining, I'll drive carelessly, of course not carelessly, but I will be very, I'll not care about the rain as such. I'll not care much about the rain. I'll be much free when I drive. Of course, when it's raining not 5 centimeter, but let's say 10 centimeter, I'll be a little more careful. If it's raining 11 centimeter, I might be a little more careful. If it's raining 100 centimeter, I may not go out. But then if it's raining something like 17 or 18 centimeter, I may go out with extra precautions. So that's all how we deal with it. So of course, there's no kind of alarm system. So there's no crisp theory that we all follow in our everyday life. There's nothing of that the theory that we follow, but unfortunately these logic systems would sometimes have. What they would sometimes have is all these systems, which of course is not the way that we normally deal with. So this is what there's some kind of a problem with logic systems that we have. Many of the logic systems, of course, that we make, they rely upon a lot of mathematical equations, where every input is related to some kind of output. So you would say that there would be a parameter that says your driving, how much you are supposed to drive, and that they say that there is a simple relationship between the inputs to the outputs. But then using some mathematical formulations, that can be another kind of a logic system that I have got. But then of course you know that practically whenever we make any such kind of system, we have to deal with lots of inputs and lots of outputs, and we have to do complex mapping from inputs and outputs. So that is what ultimately we are supposed to do. And that is what makes such kind of logic systems inefficient in nature. What we need to do is to have some kind of fuzziness introduced to solve such kind of problems, so that the relationship between the driving over here and the rain over here, that is much more smooth. And that is what we say, that we need to develop the entirely same paradigm. We need to develop exactly the same system that can use such kind of logic. Fuzzy logic is also logic. That can use this kind of logic, but the use will be much more fuzzy in nature rather than discrete in nature. That is what we are trying to do when we talk about the concept of fuzzy logic. So we'll move it from here. We'll go up to this term known as the membership functions. by mu x. If x is the input, this is what its membership degree is. So our membership function returns the membership degree of any input for whatever set it has been applied for. Now there are various, previously what I drew was simple membership function that were of this shape. Previously what I drew was such kind of membership functions. I'll just a little bit formalize the membership functions over here. They may not be of the same shape. They may take in different kinds of shapes over here. One of course is a very famous shape which is known as a Gaussian membership function, where this is the input x and this is the membership value of 1 and this is the membership value of 0. So if you plot, this is what is known as a membership curve. A membership curve is nothing but the membership function plotted graphically. If I plot the entire membership function in the form of a graph, in the form of a curve, for whatever input it has been applied, and of course my y-axis will vary between 0 and 1 because it's a membership degree. If I draw such kind of curve, what I get is known as the membership curve. So this is what is the Gaussian membership function, very nicely used, very oftenly used, and the equation is x minus c the whole square by 2 sigma square. Sigma denotes the standard deviation of this curve. Sigma is what denotes the deviation of this curve. So I can vary its shape from anywhere here to anywhere here to anywhere over here by changing sigma. If I change in sigma, this deviation would change. And C is nothing but the center. C is known as the center, where the initial value touches 1. So again, this is like a very frequently used kind of membership function where you can clearly see what happens is that the membership value is 1, it drops smoothly from 1 towards the lower regions, it drops smoothly, and then there's a curve from here to here, it drops smoothly, and then there's again where it ultimately converges to the membership value of 0. So for both the extreme inputs, it will show membership value of 0, and for the other curves, it will show a continuous range of membership value with the maximum membership being 1. Many times for the extreme cases, we make such kinds of Gaussian membership functions, which of course the input is always outside bounds, so the membership value is decreasing, and ultimately it converges to 0. Now why did I say bounds? Because again from normally when we work with such kind of intelligent systems, when we work in any systems, it is known that the inputs always lie between some lower bound and an upper bound. So for any input x, there will always be a lower bound and an upper bound. That is what I always assume, be it the neural, be it the evolutionary, and be it here. I'll make it unfortunately such kind of assumptions over here. So these are what are the Gaussian membership functions. Again, a very commonly used membership function is the triangular membership function, which I drew out in the previous case. This would be the membership value, so this would be mu x and this would be the input x. This is known as point A, this is known as point B, this is known as point C. Point A is the point where the membership value reaches 0, B where the membership value reaches 1, and C where the membership value is again 0. This is actually what I drew the previous slide. The other variant of it was when only this was drawn, and the other variant of this when only this was drawn. So what these membership functions are all about, what these membership functions and membership values are all about, these are straight lines over here. There's a linear rise in membership value as I go from A to B, and there's a linear fall if I go from B to C. A linear rise and a linear fall. So again I can say in this case my membership definition would be a 0 if x is less than equal to A, and a 1 if x is greater than equal to C. this path and this path. I need to find out this path and this path. This will be a straight equation of line. So because it's a straight equation of line, I can simply write down my x minus a upon, let's say, b minus a. If x is between a and b, this will be this line. It will be the equation of this line, and the equation of this line, I believe, will come out to be something like c minus x upon c minus b if x lies between b and c. That's what the entire equation will come out to be. That's what from the entire set we can formulate this kind of membership function. This is known as a triangular membership function. Whose curve is this? This is what is known as the triangular membership function. Again, normally used for many kinds of extremes, be it the positive extreme or the negative extreme. We sometimes plot such kinds of membership function over here. Those have got this kind of shape. This is the lower bound, this is the upper bound. This is a membership value of 1, this is the membership value of 0. Because the actual curve is something like this. It rises up slowly and slowly, and then it again converges up to 1. So it shows a transition from 0 to 1. And of course we can move around, we can change around this curve by changing its parameters. What this is known as a sigmoidal membership function. This is what is a sigmoidal membership function. The equation, I believe, is something given by mu x equals to 1 upon 1 plus a square minus a x minus c. This is what is the general equation of these kinds of curves over here. So, based on that, you can formulate many kinds of membership function over here. You can have numerous kinds of membership function that we all use for modeling in our system. When I say modeling in the system, what I ultimately mean is that there was, in our previous example, there was something known as the temperature. There was something known as the temperature over here. And because there was something known as the temperature over there, I divided it up into some regions. I divided it up into some kinds of regions, and ultimately what happened was that when I divided up into some kinds of regions, of course fuzzy regions in nature, I had to make some kind of plots. I had to make some kind of plots, and based on those plots, for any input I could find out its membership value. I could very easily compute what the membership value would be. So again, some kind of the first thing that we do whenever we are given any system. Now I have a system to make, so it is known that it has some inputs and it has some outputs. So there will be a set of inputs and there will be a set of outputs. Let me say the previous system only that I am trying to make in, the inputs were in such a case my rain and my road, and output was my drive. The same system that we took. These are what the inputs were, this is what the outputs were. We are trying to make the system, we are trying to make it as a fuzzy system. The first thing that I have to do, of course, after identification of the inputs and outputs, is to divide all the inputs and the outputs into some kinds of sets. To divide them into some kinds of sets so that I can work around with these sets. I can form these kinds of rules. So I need to divide them into some kinds of sets. Those sets are nothing but fuzzy sets. So let me say that my rain is measured in centimeter, my lower bound is 0 centimeter, my higher bound is, let's say, 50 centimeter rain. The first thing that I'll have to do, I'll have to formulate some kinds of sets. So let's say for my rain, I say a rain may be low, medium or high, or it may be the same terms that I use. I may have a low, a medium and a heavy. So let me approximately make in such kinds of curves. This may be called as the medium, this may be called as heavy, and this may be called as low. Similarly, let me say that there was something known as, this is for rain. Let me say I'll make it for load as well. Let me say load is only divided into two sets, either it's good or it's bad. So load I only divided into two sets over here, a good and a bad. So these are the only two divisions that I will be doing for the set load. So let me say that this is what the load is when it's bad, and this is what the load is when it's good. So I had rain, I had load. Let me do it for dry. I say that my dry I unfortunately use the probabilistic in nature, and just change that rule to say that dry very carefully. So my carefulness is a measure of how the dry should be. Let me say this is how it is divided. This is what is the membership function of this is what is very less careful. Let me say this is what is less careful. Let me again say this is what is careful. Let me say this is what is more careful, and let me say this is what is very careful. So these are 1, 2, 3, 4, 5. These are 5 membership functions I defined for dry. I have defined 3 over here, 2 over here, and 5 over here. So what I am trying to do is that I am trying to divide all my inputs and outputs into some kinds of sets that you have anyways done in such kinds of logic systems. Now my system is quite good in nature. I had, apart from inputs and outputs, for every input I have a set of membership functions, 3 over here, 2 over here, and 5 over here. For every input I have got these kinds of membership functions. And therefore what I do is that I try to apply some standard set of rules. I apply a set of rules. So at any time I have to find out how carefully I am supposed to drive, or in general terms what is my output for given some inputs. And to do that, what do I ultimately do is that I find out what is the relationship, what is the membership value of all these membership functions. And once I get that, I try to fire these rules. So there will be, let's say, some rule 1, there will be a rule 2, there will be a rule 3, there will be a rule n. I fire all these rules and then try to predict my output. That is what the general fuzzy system is all about. That's what the general fuzzy system is all about. I fire all these rules, and based on all these rules I try to find out what the output is. Now if such kind of a system is running entirely on fuzzy logic, and this time we call it as a fuzzy inference system. That's what we call as a fuzzy inference system. It is an inference system, so for every output it will do some kind of inference. It will generate some kind of output, and that is being driven by a fuzzy logic over here. It is being driven some kind of fuzzy logic over here. So right now what my concern is, let me take in any general rule over here, that is again for simplicity the same rule that we wrote down there. If the weight is heavy and the load is bad, then drive very carefully. If I take in the same kind of rule as we took up that time, I need to have some kind of formulation in which I can fire this rule. Based on this rule I can formulate some kind of output. So all my discussion from now on will be how is it that we can compute some kind of output when this kind of rule is fired. Let me say for this system the inputs are given, both the inputs are given, that's some value of 15 centimeter for rain and let's say a 0.8 degree for road. Let me say road, its quantity is defined by road quantity is defined by on a scale of 0 and 1. So let me say it had a 0.5. So based on 15 centimeter and 0.5, can I get in a numerical value as an output that denotes how carefully I am supposed to drive? Because again, let's say drive easiness is again defined on a scale of 0 to 1. And I am supposed to find out how carefully I am supposed to drive based on some numerical value. So that's what I am supposed to do. The entire discussion from now on would be that can I make such kind of formulations such that these rules are fired, so that these rules can be fired. So we'll do away again with this kind of basic picture that we have. We'll take this basic picture and we'll develop over it. We'll get into it. We'll see how we can develop into it. The only thing that we need to do is to have some kind of fuzzy operators. Now again, much before we study the fuzzy operator, let me introduce to what was known as the Boolean operators. The Boolean operators were, for the same example, if rain is heavy and road is bad, then drive very carefully. So what happened was that I was given some kind of input, let's say 15 centimeter in this system. Let me say it denotes that the rain is actually heavy. So my rain is heavy, computed to be true, and let me say that the road was actually bad. So the road is bad happened to be again computed to be true. Let me say that the road quantity was measured on a scale of 0.7. 0.7 denoted a bad road, and therefore this happened to be true. Now we know true and true from our Boolean algebra is nothing but true. This entire statement gets true. If this entire statement gets true, this true gets transferred over here and this statement is executed. That means drive will get true as an output. So that's how we worked about with such kind of system on Boolean logic. That is how we develop system based on some kind of a Boolean logic. So if I can make this and fuzzy in nature, if I can make the output fuzzy in nature, if I can make the input fuzzy in nature, then is when I would be able to fire these rules. Then is when I will be able to fire all these kinds of rules. So therefore, I have the term known as fuzzy operators. We look into numerous fuzzy operators that you might notice here, you might not notice over here. We'll take in multiple fuzzy operators, we'll study in multiple fuzzy operators, and in the entire discussion the thing would be that can we replace the normal Boolean operators with the fuzzy operators, the Boolean operators that rely on true and false, again the test theory, either something is true or it's false, a very test kind of theory. Can we make this fuzzy in nature? That would be what the entire discussion that would be all about. If we are able to do it, we will simply fire all the various rules and we collect the final outputs of all these rules. Aggregate them, fuse them together to get the final system output, and that's all what the system would be. So again, it's a fuzzy operator. The very first thing that we do is to study the basic three operators, and, or, and not. Because we know that any general rule that we will be facing in our system, it will have two parts. This is what is normally referred to as then. It will have two parts. Whatever lies before the first part will be nothing but a condition. This condition would be of the form if any input I belongs to set J. Any input I belongs to set J. Let me write it a little more formally. It will be of the form of input I. If any input it belongs to set Sj, that is designated for this input I. So let me say my input I, it was divided into three kinds of sets. It was divided into these three kinds of sets. And all that I need to do is that I need to work over such kinds of rules. So these kinds of conditions, this is what would be a basic condition that would get replicated over multiple times separated by either an or and or. This is what would be repeated multiple times separated by an or an or. Of course, if it is separated by and, that is what is normally referred to as an and rule, and separated by or, it is normally referred to as an or rule. Sometimes it's both an and or that come together into the same rules, and that is a really complex conditions that we use in our C programming or in our any other programming languages course. Into a practical hard rule sense, or any logic system, we again might have a complex relationship of ands and ors and the various conditions in between them. Any of them may optionally be prefixed by a not. So that is sometimes referred to as not belongs to I. So that was the general syntax would be. So we need to work out what about and, or, and not, the three basic operators. This is what is known as, this entire format, this is what is known as the antecedent part of a rule. So this is a rule here, this is known as antecedent part of a rule, and this is known as consequent part of a rule. This again a terminology we will be making some brief references to them. Both and or can take multiple operators, but we know from our Boolean algebra classes, we know from our basic understanding of the Boolean algebra that multiple inputs and multiple inputs or can be streamlined into use of multiple two input ands and two input ors. So what we consider is only the case in which there are two inputs in and two inputs in or, and that is why and or are sometimes known as the binary operators. Not takes only a single input. Again, from our Boolean algebra theory that we have got, it again takes only a single input, and that's why it's known as a unary operator. So we'll first fill in all these three types of basic Boolean operators, and we'll see how they handle fuzziness in them. How is it that I'll be able to make them fuzzy in nature? I believe for this hour I am slightly short of time, so the entire discussion over there will continue in the next hour.